Yeah, so hello, my name is Athar Srivastava. I'm in class 12 ISC, and this is today I'll be presenting on Wick rotations and applications. Mm, yeah, so wait. Yeah, so firstly, before we get into that, uh, what is a metric? So basically, a metric defines distance, angle, and geometry. For example, if you consider 2D flat Euclidean space, then the Pythagoras formula is a metric. So ds squared is equal to dx squared plus dy squared. So that defines the geometry of that space. You can find the displacement between 2 points using this formula. And so that's like the simplest example of a metric. And yeah, just a second. Yeah, so then metrics in special relativity can help us measure the interval between two nearby events. As you would know, in special relativity, the distance measured between two events and the time measured between two events can vary depending upon the observer, but the interval between the two events is constant. And so using this general formula for metrics in special relativity, um, we can find the interval between those two events, where this is the metric tensor, and the other one is the displacement in the spacetime coordinates dx, dt, dy, dz, etc. And yeah, so this would be the matrix representation of that, like an identity matrix with ones along the principal diagonal. This is a 3 by 3 version of that matrix. So yeah, and so basically, like, if I could just have the pen here. Uh, yeah, so then for the simplest version in 2D Euclidean space, you could have like ds squared matrix wise, it would be represented like dx, um, dy, then uh, this tensor. It's basically the quadratic form of the matrices, and that's just for the simplest version. And so, yeah, this would be the matrix representation, which when you expand, you get that formula. Um, then, yeah, so now there would be Lorentzian metrics, which, as you can see, it would describe Minkowski spacetime with the absence of gravity. And it has the signature of minus plus 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 or plus minus minus minus. Basically, the time coordinates and the spatial coordinates have opposite symbols, which is very consequential to this because this has very big implications for causality. Like there can be three different types of intervals. If it's like a time-like interval, then one event can influence the other event. If it's a space-like interval, then one event cannot influence the other event or cause it. And if it's light-like, then those two events can be connected by a light ray. And yeah, so that's why this negative symbol is significant in the Lorentzian metric. And as you can see over here, this is the tensor for the matrix form of this metric. And this has one time dimension, three spatial dimensions. And on the other hand, Euclidean metrics have an all positive signature with only spatial coordinates and all positive signs. So you can determine the displacement and obviously the Pythagoras theorem, and then the angles are defined by the dot product. And this over here is the matrix form, which you can use to represent it for succinctness and such, and uh, to know the symmetry. So yeah, so then we'll move on to what is curvature. Um, so curvature basically quantifies how much geometry deviates from being flattenable. So like for example, it's quite different from flat space, where if you take this curved space, then the angles of a triangle do not add up to 180 degrees, they add up to more than that. Whereas if you took a really small area on this curved space where it's basically flat, then the angles would add up to about 180 degrees. So that's how curvature is different from flat space. And yeah, as you could have seen in the diagram. So yeah, so over here, this is the Schwarzschild metric, and over here, you can see the matrix form, and the first term basically shows how gravity influences the time in that region, and the second term shows how gravity influences radially stretches space, and then the third term has with the angles. I think the azimuthal angle and such is about the geometry of that space-time region, and yeah, this is the matrix form um, of the Schwarzschild metric. And when you do, 1 second, unable to move to the others. Yeah, the Schwarzschild radius is basically when you replace the R uh, co- with 2 GM in the Schwarzschild metric. So over here, if you went and you put 2 GM, then this would become 1. So this whole term would go to 0, and this term would be 1/0, so it would become infinite. So that's why inside the Schwarzschild radius, time and space switch roles. So the same way as outside of the Schwarzschild radius, like where we reside, it would be like you can move only one direction in time, which is forwards. Whereas inside the Schwarzschild radius, you can move only one direction in space, which is radially inwards towards the singularity, and nothing can escape that, not even light. And so,
Yeah, just a second. Another point to mention maybe is when we go back to the metric, there are two ways to make the metric degenerate. That is to make it infinite in certain directions. One is when r equals 0. So since you have r in the denominator, that becomes a singularity. The second is using this. But there's a distinction that can be made between these two singularities where one of them, I mean, this is a priori, you don't know this, but you'll need to look for it. Uh, if it's just a remnant of the way the metric is expressed, or is it a true physical singularity? Turns out that r equals 2 GM is a remnant of the way the coordinates are expressed. So if you actually want to get rid of this singularity, you do a bunch of transformations and you end up at something called the Kruskal-Szekeres coordinates, and in that representation, you actually don't see this singularity. But it is helpful to see this because, as Athar mentioned, the roles switch between space and time. That is the signatures switch. Um, so yeah, that is one point to keep in mind. The r equals 0 in any coordinate system, you can't get rid of it, and that's the singularity that exists at the center of the black hole. Yeah. Sorry,
yeah,
you can go ahead. Yeah.
Yeah.
Bit of
yeah, all right.
Right. Yeah. So
Sorry.
could you just show from the metric how you decided that, or how you determined that the signatures change? Don't you get 1 0 and one undeterminate value?
we can maybe go back to that slide, Athar.
Yeah,
Yeah.
Yeah. So from here, yeah. So when we put 2 GM in this coordinate
Mhm.
system, we
yeah,
got 0 here for the time
yeah.
cases, and we are getting some undeterminate value here. So how do we know that the roles have switched? In the sense, how did we determine the signature has changed?
You go past 2 GM. That's it. That is you. So
Oh, so
yeah.
it must be more than 2 GM.
Yes. Yes. Exactly.
Okay, but and that if I have something more than 2 GM, then the first term will also not become 0,
Sorry, not
right?
more, less than 2 GM.
Yeah, I mean even right.
Yeah. So you get a
Oh, okay,
negative
okay.
there.
Okay, that's what that means. Okay, yeah, got it.
Yeah.
Yeah.
Yeah. Mhm.
Yeah. All right. Uh, so yeah, that was a diagram over here. Then, yeah, so in Wick rotation, basically, as you can see with the Lorentzian metric, as I mentioned before, the signature is minus plus plus plus, and so there's this negative, uh, negative sign in front of the time coordinate. which you can remove using analytic continuation. So you can take t and then replace it with I tau. And then if you put it over here, then the I squared becomes -1. And so the minus is lead to a plus. And thus you've turned a Lorentzian metric into a Euclidean metric, which is quite helpful for various things like quantum field theory, where you have to compute path integrals and such. And so, yeah, so that's basically what a Wick rotation is. And yeah, so there are some limitations of a Wick rotation. The first one being that it requires a global time coordinate, because if time is not defined everywhere, then it doesn't make sense to rotate time into the complex plane. And then killing vectors, which I will get into in the next slide, and closed time-like curves, which is where time loops back onto itself. And so then you can go back to the past, and so time travel is possible, but in that sense, it doesn't really make sense to Wick rotate if any of these are present, or if any of these conditions occur. Um, so yeah, so killing vectors basically show the symmetry direction of space-time. So, and along that, the metric does not change. And by Noether's theorem, uh, for each symmetry in the universe, they must uh, associated with that, there must be some quantity conserved. So for the killing vector in the time direction, energy is conserved. And for the spatial directions, the killing vector momentum is conserved. And for the rotational killing vectors, angular momentum is conserved. And yeah, so without this symmetry, it would not be possible to Wick rotate. Um, yeah, and yeah, as I explained before, without time-like killing vector, there is no consistent global time coordinate. So then you won't be able to rotate it into the complex plane, and this would occur uh, in these like inside a Schwarzschild horizon, which would be within the Schwarzschild radius, as I had mentioned before, and like a Gödel universe, where again it's possible to time travel and go back to your own past, and like expanding universes where the scaling factor depends on time. And later on, I can show you how you can get over some of these limitations, like local Wick rotation, which is instead of Wick rotating the whole space-time, you can just look at a patch of space-time where it would be basically flat. Like over here in the expanding universe, the scaling factor over here, as you can see, is a function of time. But if you consider a small enough region of space-time, then you can basically consider it to be constant. And thus you get this over here, which if you replace the time coordinate with I tau, then you can Wick rotate it and get this metric with all positive signatures. And so that's how you can basically get over um, some of these limitations of Wick rotation. And yeah,
One
Wick
sec.
yeah.
Does the previous procedure in the last slide, where we take the
Yeah.
local section, we do this, does this now no longer sort of require the condition that we have a global time coordinate?
As long as we have a local time coordinate, it would
Yeah,
work over there, right? So yeah,
right.
so I mean, it would work locally.
So now, why can't we sort of, so wait, why is it that we are initially itself choosing it to be global when we can always do this locally?
I think you are muted.
Yeah, sorry.
Yeah.
Yeah, maybe I can jump in here. Um, the At the heart of the Wick rotation procedure, you have analyticity or holomorphicity. Uh,
Okay.
and you can have these local patches, but
Mhm.
to keep them consistent with each other, you still do need the global time coordinate. Otherwise, you can only do this procedure locally.
Locally. And doing this would also just, we would not sort of force the condition that the light derivative is zero, right? We would not have a killing vector if we only do these. Okay,
Yes.
got it.
Yes. Yeah.
Yeah, and basically, as I mentioned before, applications of Wick rotation include like quantum field theory to simplify the path integrals. As Wick rotations are mainly a mathematical tool, not much of like a physical interpretation, except in like the thermal properties of horizons, and like you can use this for Hawking radiation and such, and also inflationary cosmology. So yeah, those are some applications of Wick rotation. I think
Yeah.
that's
Maybe we
all
can.
I have.
Yeah. Maybe we can even expand upon a little bit of the application stuff. Um, so there is this nice um, uh, yeah, quote that you can live by where um, statistical mechanics in complex time is quantum mechanics. And the reason why we say this is primarily because of this evolution operator. So in basic statistical mechanics, you can see distributions of particles or properties, etc. But let's start with particles, and it's usually a Gaussian that you use to model, and the Gaussian is e to the power minus beta h or something like that, beta e or whatever, where your beta is known as your thermal, I mean, it's your temperature essentially. And your E or your H is your Hamiltonian or energy, etc. Whatever. Yeah. And the reason why this happens is because of this assumption that every state is equally likely to be accessed by the particle. So if you have more states, it would be equally likely to access all of those states. And this ends up being giving you the Gaussian in whatever context you phrase it in. The stereotypical one would be keep a box and keep particles in a box, and yeah, once you have partitions, remove the partitions, etc., this is what it would follow. Now, the solution to the Schrodinger equation, time-dependent Schrodinger equation, etc., has this factor of e to the power um, minus I h t, where h is still your Hamiltonian, t is now your time, and but you have a complex time with it entering in, right? Time itself is not complexified; it just has a complex factor in the exponent. Why do we get this factor? It's just solving the Schrodinger equation. This should be one of the terms that helps you determine how the system evolves over time. Now, you see the parallels between them. And you also, when you study quantum mechanics, you also determine that when you square this the the term which is the solution to the Schrodinger equation, it gives you some sort of probability, and the from the statistical mechanics side, this distribution is a probability distribution and so on. So you start seeing these analogies, and turns out it is pretty accurate, the statement. So that's how you uh, convince yourself that what we are doing is not something purely esoteric, but actually has some connections. Now, this connection does not extend much beyond its applications in terms of its rigor. That's something that where we can all step in and think more about this. Where this would be of consequence is, as Athar was mentioning, when you try to solve path integrals in Lorentzian signature, they are divergent. But once you convert them into Euclidean signatures, you can do a saddle point approximation. of your path integrals. That is, um, let's say your uh, solution, or actually your potential has some shape, and you can approximate the solution to the particle's wave function in that potential by saying that the leading order behavior is what dominates, and the leading order behavior is what is seen at the crests and the troughs and so on of this potential. And this is in turn the exponential raise to the biggest powers and so on. And that's how that's the heart of saddle point approximations. These are also called instanton solutions, if you've heard of instantons ever before. Um, so we can only do this by Wick rotating. Now, what does it mean? And this is used in phonons and yeah, all sorts of physics, this instanton approach. Now, what does it mean for you to not have a global time coordinate such that you can't um, go ahead with this procedure? What does it philosophically mean? Is a very interesting question to think about and answer. I'm not sure we'll get an answer that's much beyond, yeah, the mathematical trick does not work, but we need to see if there is any physics behind it. These are gray areas in physics still. But yeah, that's a little bit about the application side of things. Yeah, did you guys have any questions
Uh,
Yeah.
it's not a question, but well, we can actually what if we also Wick rotate one-dimensional space with along with time? So we mess up the metric even more and make it minus minus plus plus, right?
I see.
And and I mean, in the sense, my motivation was instead of making everything plus 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 plus, what if you make everything minus 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 minus?
And then it would be
But
equal.
it would be equivalent, right? But we are then the condition that we would need there is completely different. We would require curves on space
Hmm.
to have their light derivatives to be zero,
Yeah.
and you need to have a closed loop of space, which is true, which we
Yeah.
can form very readily. Like closed space loops are
Yeah.
already there. So
Yeah.
this sort
Yeah.
of forces us to have closed time loops, which is not, well, it's a theoretical condition, right?
Yeah. So what are you getting at?
Oh, I'm just saying that the closed loops condition, which may not be satisfied by all sorts of curves on like on a manifold. With I mean, I'm saying it's better to isn't it better to deal with converting all the space coordinates into negatives?
I see. Oh, I see what you mean. So the
Mm.
existence of space-like killing curves are easier to
Yeah,
have.
exactly.
That is an interesting question. But the places where your time-like curves are usually that you find that you don't have a global time-like killing coordinate, are places where you have boundaries or the roles of space and time switch. So within a black hole, you don't have closed space-like curves. You only have closed
Oh,
time-like curves. Yeah,
oh, so to analyze
yeah,
the part inside the black holes, we are doing this whole thing. Okay, then yeah.
yeah. So yeah,
Mm, got
it is the same struggle. Uh,
yes, yes,
yeah,
got it.
yeah,
Yeah, okay.
yeah. But okay, let's probably give Athar a round of applause. Really, yeah, that was really nice, Athar. Thank you.
Thank you.
Uh, Awesome. Yeah, Athar, hope you keep joining these every Saturday. So let me just pause the recording here.